Every photograph you have ever seen of the night sky has something in common. It is made entirely of light. Whether you are looking at the glittering band of a distant galaxy, the dark lanes of interstellar dust, or the soft glow of a nebula, all of that visual information reached our telescopes exactly the same way, as traveling photons. But in the summer of 2023, scientists unveiled a portrait of the Milky Way that contained zero light. It was built completely out of particles that ignore almost everything in the universe. We have, essentially, figured out how to photograph the invisible. To understand how you take a picture without light, you need to meet the particle that made it possible. It is called the neutrino. A neutrino is a particle of matter, but it has almost no mass, and it carries absolutely no electric charge. On the left, normal light gets blocked by dust, gas, or planets. But on the right, a neutrino ignores all obstacles, passing straight through. It can travel unbothered through a solid wall of lead, a light-year thick. Its penetrating power is unmatched. Right now, 100 trillion neutrinos from the sun are streaming through your body every single second, passing straight through your atomic structure completely unfelt. That ghostliness makes the neutrino a perfect, uncorrupted messenger. It can cross the cosmos carrying a clear signal from violent events that normal light cannot escape. But that exact property creates a severe physical problem. You cannot build a mirror or lens for something that refuses to interact with matter. To catch a particle that refuses to be caught, you have to go to the geographic South Pole. This diagram outlines the IceCube detector. Instead of pointing a telescope up at the sky, scientists drilled dozens of holes 2.5 kilometers deep into the ancient, highly compressed Antarctic glacier. They lowered over 5,000 sensitive light detectors into the ice, mapping out a solid cubic kilometer of instrumented space. Out of the millions of neutrinos constantly passing through this grid, exactly one might occasionally clip the nucleus of an atom in the ice, shattering it into a spray of fast-moving charged particles. Those new particles tear through the ice faster than light itself can travel through that same medium. That creates Cherenkov radiation, a faint blue glow that acts like an optical sonic boom. The sensor grid records exactly when and where those flashes ripple through the ice, allowing physicists to trace the original particle's path. Because they could not manufacture a traditional lens, they had to turn a cubic kilometer of the Earth's own geology into the largest particle detector in history. IceCube successfully recorded over 1 million neutrino events, but almost immediately the team ran into a wall. Nearly all of those signals were local, a constant blizzard of atmospheric noise created when cosmic rays slam into Earth's own sky. Finding the true deep space messengers hidden inside that atmospheric chaos was like trying to pick out a single whispered word from the middle of a roaring stadium. Looking at this visual, you can see how they solved it. The team trained machine learning neural networks to precisely recognize the extremely subtle signatures of galactic neutrinos. The algorithms filtered away the local noise, isolating the true signal. What remained was a yield of exactly 60,000 carefully sifted particles, painstakingly gathered over 10 years of continuous observation. The galactic signal was there the whole time. Humanity did not pull it out of the dark by building a physically larger lens, but by building a smarter way to process the data. But this raises an obvious question. Why would our galaxy glow in neutrinos in the first place? It comes down to violent collisions happening out in the cold between high-energy cosmic rays and massive clouds of interstellar gas. When a high-speed proton slams into interstellar gas, it shatters into pions. These instantly decay into two things, gamma rays and neutrinos. Wherever the galaxy produces gamma rays, it produces neutrinos. Overlaying new neutrino data onto existing gamma ray maps, the regions lined up perfectly. Now, you should know what this final image looks like. It is not a sharp, crisp photograph like you'd expect from the Hubble Space Telescope. It is a faint, blurred, incredibly grainy smudge. But the blurriness does not matter. This image is the modern equivalent of the very first smudged daguerreotype. Its power lies entirely in proving that capturing a portrait of the cosmos using solid matter instead of light is actually possible. For thousands of years, everything we learned about the universe beyond our solar system arrived strictly as electromagnetic radiation, just waves rippling through a field. Neutrinos have mass. They have physical substance. By successfully capturing them, we are looking at our home galaxy through a medium completely separate from light. This opens the door to what astrophysicists call multi-messenger astronomy. Light shows us the surface spectacle of a star. Gravitational waves show us the violent physical motion of massive objects. And neutrinos punch straight out of the dense, hidden cores of the cosmic engines themselves, places where the light is trapped forever. By combining these separate channels of information, humanity is gaining true three-dimensional depth perception of the universe. If our very first blurry look through this new window immediately showed us the Milky Way in a way no telescope ever could, what else is out there, waiting in the dark, that has been speaking to us in ghosts all along? If you want to keep exploring the deep mechanics of the universe with us, take a moment to subscribe and share this video with someone who loves the night sky. There is always more out there than meets the eye.